Well, good evening, Dr. Mark Miller. Thank you once again for your response in the emails. My name is Marcelo Correa da Silva. I'm a PhD student from the University of Goiás in Brazil. We're working with indigenous cattle breeds. One of them isn't actually a breed yet, but very interesting cattle. And we're using some population genetic approaches, working with SNPs to understand basic and preliminary issues. So this is our rubber band, not the rubber band method that you gave us in your software, but the other one. We're using different sizes of distance classes, and the spatial autocorrelation was very interesting for us. We used 5 distance classes, and we saw that they, well, independent of how many distance classes you're using, they're always mainly significant. But what I wanted to show you is that I'm not using the negative spatial autocorrelation term. I'm just saying that the strength or the effect of spatial autocorrelation is stronger. I don't know if you agree with that or not, but I'm not using negative spatial autocorrelation when I'm talking about this, for example. Okay. Well, basically we saw some intermittent patterns or some patterns of stabilization. We didn't see a very strong signal or a cline like Huxley would call it. This is an example with 15 distance classes. This effect here we believe is stronger. We think here it's random. It's got a random pattern, but it's difficult to point out the geographical distance that is useful. But we did find that with less than 290 or 300 kilometers, the effect is normally stronger. Okay. This is showing an intermittent, the colors just helping us to see quickly that the pattern is intermittent. There's not a cline, but there are significant classes, 25 distance classes here, stronger pattern or stronger effect of spatial autocorrelation. We're not using negative spatial correlation anymore. We're not sure if this is an isolation by distance or an Iceland model, but still, here we're just showing in yellow the counties. We're comparing county with counties and seeing where the distance is less than 300 kilometers, showing there's a risk of pseudo replication or false replication. Okay, well, we're working with signatures. We're very happy because the Bayesian approach with the software structure is showing us that this population here in blue, the genetic population in blue, and also the heterozygosity we calculated, they are consistent with the results from Monmonier. Here we're seeing the first barrier, or the first genetic discontinuity, is in the center of the polygon. That's consistent with this population, and we know who these guys are. The second barrier or discontinuity is this one over here, and we see a third one here and a fourth one here, and we see a fifth one over here. Well, we cross-checked these results with the Bayesian approach, and happily they're very consistent. We're working with different number of SNPs when we're using the Bayesian and the Allen's space, but this signal here is consistent with the first barrier we saw, and the other patterns are as well. Well, we also checked for multidimensional scaling plots using the our software, and we saw things that can be comparable. We also checked for different sampling schemes, and when we take, like we have a first, a two, a third, a fourth sampling scheme, that means taking away some populations and throwing in away other ones, keeping ones just to see what happens, and the genetic distances between the sampling schemes we worked are significant. So that's surely a matter that there are some populations that are different than each other. We use the mantle test in analysis in space as well, and we saw that not more than 23.04% of the genetic diversity can be related to the spatial dependence or the geographical distance actually that we're talking about. It's predominantly linear, but the R square here is very small. It doesn't matter if we're using the log or the simple geographical distance. It's always small. This is when we're not using the Delaunay triangulation, which gives us that the middle, we have greater peaks in the middle here, a discontinuity here. Okay. We did find that working with different sampling schemes, your 3D shape, landscape shape, it's sensitive to actually signalize that the main pattern doesn't change, but it does show differences in the peaks. So when we delete a certain herd, things get a little different. The pseudo-slopes approach showed us, of course, a very different pattern, but it's showing that the edges have differences. Kalu, sai daí. And in the middle, the pattern of genetic distances in the middle of the landscape shape is different from the edges. Okay, we think that it doesn't give us much information because there are big genetic distances when we consider small geographical distance. Yeah? Anyways, when we use the Delaunay triangulation and when we use all the observations, we did find that the Delaunay method gives us a smoother shape. Okay, in the middle here we have like a plateau. We are very happy with the results. I want to thank you very much. Do you agree with what I'm saying or not? I'm very happy that you left the software for us to use, and it's been very exciting to learn and reading your papers and other people's papers. It's been an amazing experience. Thank you very much, Dr. Miller.